In this activity, you're going to derive the ODE model of a simplified car suspension model. So in this case, mass 2 here represents the mass of the vehicle. The mass 1 represents the mass of the combined wheels and axle system. The suspension, so these springs and dampers here are represented by the spring and the damper here. And then the wheel has some springiness, and that's represented here by the wheel. And so one of the kind of interesting things is, even though the car is moving forward like this along the road surface, this velocity really doesn't have a whole lot to do with anything that we're going to model in this particular activity. But the interesting thing here is that as the car moves, this reference, so essentially the road surface here, is possibly going to not be flat. So you can imagine you have a pothole, you have a speed bump, you have any sort of irregularity in your road surface. That is actually what's stimulating this whole system. And so if this road surface was completely perfectly flat, you're on those salt flats, then this system is going to essentially reach its resting position, and it will just kind of stay there. So nothing's going to happen. So it's actually the action of this reference, this R value changing up and down, that then jostles and manipulates what happens in this combined system. So this often takes students a little bit of time to kind of puzzle this one out. If you're having a really hard time getting through this one, what I'd recommend is going back and taking a look at that vertical spring mass damper example. It is very similar to this particular activity, but now we have this extra mass and a coupling term. So I'll give you a few moments. I really recommend that you try to solve this one all by yourself and then take a look at the solution. So solve this out, chat with some friends, and then move ahead once you've done that to compare with my answer. All right, so you've managed to make it through. Very similar to the vertical spring mass damper. The key idea here is to first draw your free body diagram. In this case, we have two masses. So in this case, I've got mass 1 up here, and so that's this bottom mass. And again, the really important thing when you're dealing with these free body diagrams is to make sure you know which direction you're drawing your arrows, and kind of be purposeful about that, and then think about what it means for these variables x and y to either be positive or negative. So the arrow here indicates that y being positive goes up, and this arrow means that x being positive also goes up. And so what you want to think about is, what are the forces that this block is going to feel when x becomes positive? So when x becomes positive, you're going to be stretching this kW spring. So it makes sense that the force then would be pulling down. And so that's the reason why I've personally made that choice to put that down and then write the force such that when x is positive, that's a positive force. So now the positive x direction then pulls this block down. Likewise, we've got the spring force and the damping force. These are actually going to pull up. And in this case, these are going to pull up when y is positive. And so that's why I've written these as pulling up, and y is my first term, that it's positive. So again, if you wanted to, you could switch these arrows around and then switch these two and essentially make that, for example, x minus y, but with an arrow going down into the block. So that's essentially the same. So once you have your free body diagram, the beauty is that now you can say that it's the mass times the acceleration. So the variable that's describing this block is x, so it's x double dot. And that's going to be the sum of all the forces on this. And so in this case, if the arrow is pointing down, that's pointing in the opposite direction of x, that means you're going to have this minus sign. If these are pointing up, then that means that this force provides an acceleration in the positive x direction, and so these come in with positive signs. But what you should be looking for is the fact that the damper causes these derivative terms, and the springs should not have derivatives on them. And in this case, it makes sense that the force on the spring down here is going to be related to the difference between X and R. And here, the spring and the damper, this is going to be related to the difference between X and Y. So again, if X and Y move together, and they move the same amount together, then there is no change in the force here. But if X and Y move and Y is getting bigger and X is staying the same or not changing very much, then that means that this is, say, stretching the spring and stretching the damper, and so that will cause forces. So similarly, you can write your block diagram or your free body diagram for mass 2. In this case, it just has the two forces that are attached at the base here. In this case, I'm going to write it using the same term, so it's Ks times y minus x. And so here then I've placed the arrow going down because as y gets bigger, that's going to stretch this spring and pull the block back down. And the same thing happens here. And so the important thing about a damper is that this is really describing resisting the rate of change of y and x. So these are relative velocities, not relative displacements. So again, these both enter going the opposite direction of y, and so they both come in with this minus sign, and you set that equal to mass times acceleration. So what that gives us, if we just do a little bit of reorganization, pulling the double dot terms to the left, then we can rewrite this, and we're going to see why we rewrite it later, but we can rewrite this like this. But you could leave it essentially in these two equations as well, and that's a very valid model. This particular description sets us up for doing some stuff that we'll do in the next classes.